So it's my pleasure to introduce our next speaker on day two, Dr. Fatih PORIKLI from Qualcomm Technologies will give us a talk on on-device generative AI. Over to you.
Thank you so much. Good morning from San Diego, and thanks for having me. Generative AI models such as ChatGPT and Stable Diffusion are disrupting traditional technologies from search and content creation to automation and problem solving, and are fundamentally shaping the future user interface of these computing devices. As generative AI adoption grows at rapid setting speeds and computing demands increases, battery-powered on-device processing for generative AI is becoming more important than ever. Just like traditional computing evolved from mainframes to today's mix of cloud and edge devices, AI processing will be distributed between them for AI to scale and reach to its potential. So today I'm excited to talk about Qualcomm's role in making on-device generative AI possible and many advanced technologies that we have been developing recently to make on-device battery-powered on-device generative AI possible, fast and efficient. And in this talk, I will go over why on-device generative AI is important. Key are full-stack AI optimizations, which is the approach that Qualcomm takes to solve complex system problems, full-stack AI optimization for diffusion models. I will talk about Stable Diffusion, and also a language model, LLM Llama 2. And these and many more are actually available at our AI Hub. At Qualcomm, we cover the entire spectrum of AI research and development. We categorize our research into three overlapping areas. Fundamental research looks to furthest out into future and is generally more foundational. Examples include everything from latest neural networks to generative AI and learning with or without labeled data, annotated data. Platform research generally applies to improving AI models across the board, such as distillation, quantization, compression, hardware, software, co-design, and so on. This research then falls into tools that allow AI to run efficiently on hardware. Applied research is where we incorporate AI research results into specific use cases like on-device learning, computer vision and perception, and many things we do with speech and all other modalities. For AI in general, on-device processing is beneficial for a number of reasons. For instance, privacy. Users don't want to have to send their data to the cloud every time they run such models. Reliability and latency. Users, like in a fully automated driving scenario, need the data to be processed locally on device in real time. Cost. Running such models in cloud costs money, both processing but also the data transmission efficiency and bandwidth utilization, and even with the emergence of high-speed, let's say 5G, 6G connections, economically speaking, processing at the edge device really can make a huge difference. And energy, of course. Edge devices can run generative AI models at a fraction of the energy, especially when considering not only processing but also the transmission and personalization. More importantly, on-device AI can make more personalized experiences possible, from digital assistants to be customized to user expressions, preferences, content, without sacrificing privacy, to all other type of use cases. And of course, the rise of generative AI with foundation models is driving a new wave of use cases around content creation, search, and productivity across different device categories, for instance, including smartphone, laptop, and PC, automotive processing platforms, pipelines, XR devices, as mentioned before, robotics, and IoT. And our architectures enable generative AI to provide new and enhanced user experiences across all these segments. Let me also mention that with billions of AI-capable phones and PCs and all the other devices in users' hands. Today, the potential to tap into the large amount of on-device processing for generative AI is already significant and poised to grow steadily in the upcoming years. A key question here becomes which generative AI models we can run on device with appropriate performance and accuracy. Generative AI models, unlike their conventional counterparts, require substantially more computations and parameters. The great news is that such models, generative AI models, are getting onboarded at edge devices as the processing capabilities continues to improve. Models like Stable Diffusion with over 1 billion parameters are already running executed on phones with performance and accuracy levels similar to the, let's say, cloud version. And many LLM models from 7 to 10 to 13 billion parameters or more are slated to run on device in the very near future or already running that I will show. By the way, these numbers I put here assumes integer for quantized parameters, and ResNet 50 here, for us to give you an idea, is 3.8 gigaflops. In comparison, ST requires 400, ST 1.5 actually 400 gigaflops. Let me also touch upon the full stack generative AI optimizations with an example. In this case, I will talk about diffusion, what diffusion is and how it relates to AI. Diffusion has been used for image generation, content generation. Forward diffusion is where we start from a nice clean image and then incrementally add noise. This is how the diffusion model is trained initially with both such clean and noisy images and also often accompanying text descriptions to condition them. Reverse diffusion process starts with a noisy image. That's what we run on device, and incrementally removes the noise, estimates and removes the noise until we reach a nice, clean target final image. This is for image generation. Stable diffusion, as the name implies, generates images through this reverse diffusion process based in the given text prompt conditioning. You can see the architecture of stable diffusion on the right. The unit is repeated many times, many steps, denoising the image for a number of steps until the output is created. The unit is the biggest component here in terms of the computational load. It requires many steps also, let's say from 20 to 50 to, in some cases, even more, to generate high quality results. To reduce these compute requirements, we did full stack AI optimizations and significantly reduce the latency. Let me focus on the unit. So here you see a kind of simplified unit architecture. To reduce the amount of computing required per unit iterations, we develop an efficient architecture design, many of them actually, through pruning and knowledge distillation. For instance, we prune the attention blocks in the first layer of the unit, which says significant computations goes down from 800 to 600 gigamegs. In addition, reducing the compute, this and many other architecture optimizations allow reducing peak memory usage. And also, of course, it doesn't come free. This kind of reduction in computations we compensate by doing knowledge distillation. And also, maybe I should mention that the compute required for stable diffusion is directly related to this number of steps, denoising, diffusion, implicit DDIM models. We use step distillation where we teach a student network model to achieve in one step, one unit iteration. I mean, what the teacher achieves in two, for instance, or multiple steps, while maintaining the accuracy. For example, in this case, the student model unit learns to achieve the same output in as two sequential units of the teacher one. So we can go from 16 to 8, then 8 to 4, 4 to 2, significant increase in speed and reduction in compute. In our full stack optimizations, there are also several other distillations in addition to this state distillation, for instance, there is guidance condition distillation. Guidance is given text prompt, for instance, to this model to generate something based on the user's kind of text input. Stable diffusion needs to run it twice with and without such conditioning. So what we also distilled is putting them together and not having to run this unit twice, but only once. And also to make this distillation more efficient, we switch from epsilon to velocity estimations, in addition to, like I mentioned just before, different architectural optimizations. So as you see, there are some metrics, performance metrics here for CLIP. It's a surrogate for measuring the similarity between an AI-generated image and its corresponding text caption. Higher is better, and our phase stable diffusion almost matches the baseline stable diffusion in that case. For FID, freshet inception distance, another surrogate for diversity, lower is better. We have some data here, but this is because test has been trained with less than 20 times smaller data set, and also only 2.6% of the GPU hours that the original stable diffusion trained with. Overall, generating high quality images under a second is the result that we achieved. Like maybe here, it will show that this is a demo running on a Qualcomm device. And this is at the time when we showcased last September, October, it was the world's fastest text-to-image generative AI model on the phone. And as you can see, kind of it takes half a second to generate a 512 image from our model. We have larger image generating models already in the pipeline, and I will talk about them very soon, hopefully. The full stack AI optimizations that we did for stable diffusion applied to any language, vision, or large vision models, LVMs, and other diffusion models in general, even LLMs and LMMs, multimodal models. The optimization we did for stable diffusion includes system optimization, like designing an efficient diffusion model through architecture optimization and knowledge distillation, then model efficiency itself using quantization-aware training with knowledge distillation for pruning of attention blocks, for instance, resulting in a more accurate model with reduced latency and power usage. Quantization not only increases performance, but also saves power by allowing the model to efficiently run on our dedicated hardware. There's also like compilation optimizations. We are using Qualcomm AI engine to optimize onboarding of large graphs and minimizing memory spillage and hardware accelerations. Actually, we take advantage of the specific features of attributes of our NSPs, the Snapdragon 8 third generation mobile processor. To optimize, now let me talk about the language models. To optimize a large language model, LLM, is good start. It would be good to first point out where is the bottleneck. LLMs are autoregressive models, and which means that future output values depends on its previous values. So processing needs to be sequential. It is difficult to parallelize that. So LLMs generate a single token, which is a unit of text to generate language such as words per inference. Each parameter of the LLM must be read to generate a single token. This is the bottleneck. So we have to go over entire model to generate a single token. For example, Llama 7B, it has 7 billion parameters. That model must be access read to generate a single token, which means a lot of bandwidth is required. Memory access is the bottleneck for LLMs for that reason, which means that they are highly bandwidth limited rather than compute limited. The previous things I showed, there were a lot of computation required for even a simple image generation, but here our challenge is bandwidth. So I will show you in the next slide, following slides, how this insight helps to accelerate an LLM. Okay, I had this demo. So this is the kind of sequential process of the LLM, one word, one token at a time it generates. So let me just switch to the next slide. To optimize an LLM, keep in mind that they are trained floating point FP16. We would like to minimize the bandwidth. We would like to shrink an LLM memory footprint. For example, switching from FP16 to int4 reduces the model size 4 times. That reduces the memory bandwidth, storage, latency, and power consumption, many things at the same time. However, quantizing to a 4-bit integer model can be challenging due to several reasons. For instance, accuracy loss, and also, in many cases, the training pipeline, the data sets are not available. So, regarding to address this, we use quantization-aware training with knowledge distillation to get a smaller and kind of int4 model. With knowledge distillation, we are able to reduce the bandwidth footprint while solving quantization challenges of maintaining model accuracy and lack of original training pipeline data. Our results are very close to the original models. In this case, for instance, just less than 1 point drop in perplexity, which is a typical metric for LLM generation capability, and less than 1% drop in accuracy for reasoning tests. Since LLMs are memory bound, we can use a speculative decoding method to speed up the token rate by trading of compute for bandwidth. To improve the user experience, there are 2 models here. Speculative decoding works by having a draft model, which is significantly smaller than the high accuracy target model, original model. And what it does in this example, it shows that the draft model takes 4 tokens, generating 4 tokens. Target model then processes all 4 tokens coming from this draft model in one pass, one as a batch, which means that the parameters of the model are read only once. The target model decides which tokens to accept. Then a draft token is rejected, it is discarded together with the following draft tokens, and the target model samples a correct one. And when all draft tokens are accepted, the target model samples an additional token. So a good draft model predicts next tokens with high acceptance rate. Designing a good draft model is a trade-off between this accuracy and the model size. So as you see here, in this case, the draft model is running actually on CPU, and the bigger, let's say, Llama 2 model, in this case, running on NPU, NSP. So we actually do more compute, but kind of it is much faster in this case. So then we minimize the overall bandwidth. So when we do that using speculative decoding and other optimizations I didn't mention, we are able to achieve SOTA performance on device for Llama 2 7B. In this case, the model approaching more than 20 token per second TPS on Snapdragon 8 Generation 3 device, and more than 40 per token per second on Snapdragon X Elite device. And of course, our full stack AI research covers the entire ecosystem. For instance, LLMs are the key component of an AI assistant that enables basic chat and chat assisted apps on device. The user interface can be voice or text, with voice being more convenient. Of course, in many scenarios, we use Snapdragon voice activation and ASR model for speech recognition. Based on the prompt, there's an orchestrator. Orchestrator works with a mini language model to classify the task. Then through APIs to the internet, for instance, it could be a travel planner, or to the user data on device, it provides improved prompt to the target LLM, like the optimized one that I just showed with speculative decoding, for a better response. So the chat with AI assistant processed in this manner clockwise, right? So in addition to that, this is one of the examples of these AI assistants running on a smartphone. And I can say that this is the fastest Llama 2 7B on phone. As of now, we demonstrated in last October. And also this is also the world's first speculative decoding running on device. And this is not everything we have. Let me also show a large language model, large language model with input image input. So these are also called as large multimodal models, LMMs. And we demonstrated world's first LMM on the phone. In this case, for instance, user gives a picture and asks questions like a chat, and then the model tokenizes the input image or video, any type of model. And of course, this dialogue is through speech interface, but I don't have the audio feed today. So this was world's first LMM running on the phone. I think since I'm running off the time, I will just very briefly say that we can also run LoRa versions of this, let's say, stable diffusion very efficiently on the phone. We don't need to kind of retain all the LoRa fuse models. Many of them, we can drastically reduce the memory required to retain these models. Yeah. And that was also another demo we showed at MWC recently. With on-device AI being reality now, we enable developers on last month, February 26, we introduced Qualcomm AI Hub. It's a central location for AI developers to access resources aimed at, this stable, Snapdragon and Qualcomm platforms. It's a key enabler of fully optimized models. For instance, developers, users can select the model and framework, then target platform, and then they can deploy using a few lines of code and can test on cloud and on device. And this is my last slide. I like to summarize these key takeaways. Running generative AI models on battery-powered edge devices has many benefits, and Qualcomm is pioneering and enabling generative AI to scale, empowering users and developers to access and run generative AI models on edge devices. And I'm very excited to say that many more amazing and wonderful generative AI models are coming to our customers and everyone actually through AI Hub very soon. Yeah, thank you so much.
Excellent. Thank you very much, Fatih. Thank you for the talk. Thank you, Qualcomm, for the demos as well.
Huge thanks to all of our partners. Wouldn't be possible without you. We have AI Zip, Arduino, ARM, BrainChip, Edge Impulse, which is where I work, Embed UR, Efficient, Greenwaves Technologies, Gravetti Inc., Hymax, ImagineMob, Infineon, Inotera, Nota AI, NXP, P&G, Corvo, Qualcomm, Renesas, Schneider Electric, SensiML, Sony, Silicon Labs, ST, Synaptics, Sentient, and TDK. These are our strategic partners. We also have executive strategic partners, Qualcomm AI Research, who are advancing AI research to make efficient AI ubiquitous, Sentient, who are accelerating your edge compute, making edge AI a reality, and our platinum strategic partners, Embed UR, Atrios, who deploy vision AI at the edge at scale with Sony, and our gold strategic partners, ARM, building the future of TinyML, Edge Impulse, the leading development platform for Edge ML, Infineon, driving decarbonization and digitalization together, and Renesas, who are enabling the next generation of AI-powered solutions that will revolutionize every industry sector. ST Microelectronics, who provide extensive solutions to make tiny machine learning easy. Synaptics, who are engineering exceptional experiences. And our silver strategic partners, AIZip, Arduino, BrainChip, Efficient, Greenwaves, Gravetti, Hymax, ImagineMob, Inotera, Nota AI, NXP, P&G, Schneider Electric, SensiML, Silicon Labs, and TDK. Thank you to all of you. And that's to wrap up our session here. Huge thanks to the audience and all of the presenters. We've had an amazing couple of days of insights and inspiration to go forward and build great things. So thank you so much, everybody, again, and I hope you enjoyed it.